From a remote sensing point of view, what we can measure is this water limit readings. And here is the downwind E readings right above the surface from the sun and the sky. So that's what we call ED. Then we define this so-called remote sensing reflectance, which is a ratio of this LW to ED. And here are a bunch of examples of the spectrum of remote sensing reflectance. Okay. So the objective of ocean color remote sensing is not simply get this spectrum. We want to get environmental information from this spectrum. So that's then with that, then we can do many other applications. So how to get this environmental information like chlorophyll or suspended sediments, those things. So we need have ways to basically to calculate algorithms. So here are the inputs, either water limit radiance or remote sensing reflectance. That's what ocean color satellites can provide us. The outputs are our goals, like we want to get chlorophyll or get IOPs. So what's in between, I call a bridge. This bridge is just this algorithm. There have been many algorithms in the literature developed in the past decades. We can divide that into two big groups. One is called empirical, another called semi-analytical. For empirical, we can also separate that as explicit or implicit. Explicit based on those regressions, you can see the function, you can see the coefficients of those functions. So that's why I call it here explicit empirical. Implicit based on like this is the AI or neural net or machine learning. So where you do not see equations, no equations, it's all hidden in the computer code basically. But fundamentally, empirical is the same thing. Basically, you just need data, okay? And you don't need what we have been told this morning and yesterday, these fundamentals of radial transfer, fundamentals of absorption scattering. You just, as I have data, okay, you either do your regression or you need a computer to do it. So for that part, it's basically we don't, I'm not sure we need any training school for like this, because this training is really trying to get to understanding of ocean optics and ocean color remote sensing. So that's a data-driven empirical. So that I will basically little bit touch on that, but I will not spend the time on this. But I will spend time on the semi-analytical. This can have algebraic solutions, lookup tables, optimization, and on. But for this, we have to understand like the IOPs, the characteristics, and the mechanism behind it. Basically, we need these bioptical models. So that's a key difference between empirical and these semi-analytical algorithms. For semi-analytical algorithm, we may further separate into two classes or approaches. One is I call it bottom-up strategy. Another is called top-down strategy. I will get to details of both. Here are the, I bet you have known very well, so this kind of empirical algorithm. Here is chlorophyll-centered band ratio algorithms. You can see there are many regressions. Okay, if you ask why, actually there's no why. It's just that data. That data shows, okay, the best regression is like this. You can see these regressions are not identical, okay, even for the same input, because these are fundamentally data-driven, okay. They have their data, fits this kind of regression better, so they use this kind of a formula to get a regression algorithm. So that's why you can see many of these. But generally speaking, you see it's a ratio of this blue to green, okay, 443 to 565, or 490 to 555, 443 to 555. It's basically a blue-green sort of kind of ratio for this. So the reason is this remote sensing reflectance, here's a blue, here's green. You can see when you have lots of phytoplankton, it will basically pull down remote sensing reflectance at the blue bands. But at the same time, because of increased scattering, you have more sort of kind of a contribution to the BB, as Mike has told, as a back scattering. So you have more BB, and remote sensing the BB over A sort of function I will show later. So that will increase the green. So this ratio pretty much give a good indication of the abundance of phytoplankton. So that's why you can see many of these algorithms use this kind of blue to green ratios. Another approach is very clever by Chuanmin Hu. He, instead of using band ratio, he used the band difference. 3 band. One is the blue, another is green as red. So this CI basically is a band difference of remote sensing reflectance. Basically, one of these measures is you have a straight line from the blue to red. Then at 555, you count, basically calculate this height or the difference between the measured remote sensing reflectance and this straight line at this 555 wavelengths. So use this, he calls CI, I call it band difference, use this band difference as an input, then can calculate the basically also estimate concentration chlorophyll. But this is also basically empirical, okay? This is good for oceanic waters for chlorophyll up to about 0.2 micron per cubic meter. The key sort of kind of importance or usefulness of this band difference is can get much sharper images, because from remote sensing, satellite remote sensing, after atmospheric correction, there's always noises, okay, in the remote sensing reflectance. And the RS555, as you can see here, this value is very small. In the open ocean, roughly about 0.002 per sterling. So a tiny error in the atmospheric correction can cause large error at 555. They do a ratio of 443 to 555, basically that will enlarge this error at 555. So that's why, okay, for this band ratio derived chlorophyll, you'll see noisier, okay, product of chlorophyll. But use band difference, you see much sharper images. So this basically give us enhanced image product. The value generally is about the same, but the image product with the band difference is much better. So with empirical, we can actually do anything we want as long as you have the data. So basically here shows that with band ratio, we can also get total absorption or phytoplankton absorption. Again, it's just simple regressions. Also, we can also use the band difference. This is the same band difference, 555, 443, 670. We can use that to get a total absorption of 440. So you also use the band difference as an input to estimate absorption by these kind of empirical approaches. And by this way, it seems we can extend that to about 91% of the global ocean. So here, basically, is a mathematical way to show the value of a band difference versus band ratio. As I mentioned, after satellite, after atmospheric correction, remote sensing reflections from satellite always have these uncertainties, delta lambda. And the delta lambda from atmospheric correction, in general, it's kind of a wavelength dependent. So it's covariant for different bands. As long as this delta lambda has this kind of a relationship, y lambda plus x, then the band difference from satellite is the same band difference of true RS. So that's why we can get a sharp image product from band difference than band ratio, because band difference can cancel this out, but the band ratio will not be able to cancel this out. Okay, that's more about the empirical algorithm. Also, as I mentioned this morning, as Mike mentioned moments ago, we have any questions? Yeah, just simply stop me. I'll be happy to answer any questions. Okay, so for mechanistic algorithms or physics-based or we call it semi-analytic algorithm. This is the remote sensing reflectance, LW by ED. So to use this as input to estimate or calculate IOPs or chlorophylls or other properties, we first need to know, okay, how this RS is related to the biooptical properties of the water media. Fundamentally, everything goes to the radiotube transfer equation, as L is radiance, C is the beam attenuation, beta is the volume scatter function. Here, the in-index scattering is omitted. So that's a fundamental sort of kind of a governing relationship for ocean optics or ocean color remote sensing. If we define remote sensing reflections below the surface as LU, right below surface, divided ED below the surface, this is the exact solution, okay, which has no in-index scattering, okay. Basically, it's for the elastic scattering part. So this is Zanimier's 95 exact solution. Basically, in another way, so rewrite this radial transfer equation after some simplifications, okay. But still, this is not directly applicable to our inversion. So, Mike, I think you showed this a moment ago, but here this is kind of a simplified equation of this one, okay. Basically, it has this beta inlet, or A and BB, and also include a few of these FL and this BB sort of kind of backscattering ratio inlet. So that's one of the approximations of this exact solution. There are many other approximations for this subsurface remote sensing reflectance, like based on Albert Mobley, this fourth polynomial. Parker-Rudick also fourth polynomial. Okay, but this one has different view angles. I think this one is a different wind speed, I think, if I remember correctly. And here's another one, okay, by Wander, Wold, and Parker-Campos. So these are different sort of kind of approximations of that exact solution. Here are more, okay. Morales, okay, here's also the BB over A plus BB, as Mike mentioned before. Basically, the whole remote sensing reflectance is proportional to BB over A plus B. Basically, A plus BB shows about attenuation. BB shows the photons back scattered and get to the going upward and then enter the space. Think about, I always said, if BB is 0, forget it. We cannot do remote sensing because then will be water is completely black. There will be no signal. So that's why we have this generally BB over A plus BB sort of kind of relationship. Morel just tabulated these G parameters, okay, for different wavelengths, for different chlorophyll, for different view angles and sun angles. Commonly used, it's a Gordon's approximation. It's a quadratic function, which is BB over A plus BB, okay, with these two sort of kind of constants. And this RS is basically, it's, with this pi means it's completely going upward, so it's kind of vertically down. And we did separately or differently, divided this BB into BB water over A plus BB and the BBP over A plus BB. The reason is that, as I mentioned this morning, for the backscattering in the open ocean, actually in the blue part, it's water molecules dominant. It has its phase function. In the longer wavelengths, okay, it's actually particles dominant. So this way can separately accounting the phase function effect of the phase of the molecular scattering and particle scattering. So these are the basically these are the approximations used in mechanics models trying to get the inversions. But that's below the RS. Remote sensing gave measures above RS. So we have to get this below and above get connected. Above RS is LW over ED. ED0 plus, and ED0 minus has a relationship with the ED0 plus. Plus here is upwelling radius get reflected back into downwelling radius. So this is the ED0 minus connected to ED0 plus. And the LW versus LU, it's following this relationship. This is transmittance. This is the refractive index of water. So put these together, we can get above surface remote sensing reflectance. It's a TE, that's the transmittance of downwelling irradiance. This TL is the transmittance of upwelling irradiance. This is below surface RS. This gamma is the internal reflectance of the LC interface. This R is irradiance reflectance. So then we can get the below and above connected. So for nadir angle, this pi, this roughly based on hydroelectric simulations, this part is roughly about 0.52. This R and gamma R roughly is 1.7 times small RS. So now you see, okay, below surface RS and above surface RS are connected. Then how to solve? So this RS is what we can measure or obtain from satellite or airplane remote sensing. Then we want to use this as input to solve IOPs or in-water constituents. So as I mentioned a moment ago, there are two strategies to do this. One is bottom up. It's a, let's say, bus. Basically, that means that is, we assume we know the spectral shapes of the optically active components. We just build a remote sensing reflectance, trying to match that or measure remote sensing reflectance. Another way to do this is top down. Basically, in this strategy, we only do the things we want. We do not model each component as the bottom-up strategy. I will get to the details of both. First, we have to really have a good understanding for ocean current remote sensing, the challenges we are facing. Okay. Remote sensing reflectance is a spectrum, no matter it's 5 bands, 100 bands, 200 bands. So it's a spectrum. This remote sensing reflectance spectrum at least have 2 spectrums to make it. One is absorption spectrum, another is a backscattering spectrum. We spell it out. A has at least 3 components: the A water, the pure water or pure sea water, phytoplankton pigments, and detritus and gap stuff. There are some. So A has at least 3 components. BB at least have 2 components. One is the BB water, another is the BBP. Okay. Yeah, for remote sensor, there are many bands. Next, we have N bands. Then each band has an equation like this. So N bands, we have N equations like this. But for each equation, we still have APH, ADG, BBP as unknowns. So fundamentally, the number of unknowns is much greater than the number of equations. So no matter you have 300 bands or 3 bands, it's the same issue. So that's a yield formulated math problem. As we learned that from high school or college algebra, we have too many unknowns, which when there are more than equations, there'll be no solutions, right? So, but we are remote sensing guys, right? We do want to get some solution. We're going to get some results. So what do? We have to either increase the number of equations or decrease the number of unknowns. Either way, it's the same thing. Okay. So here is again the bottom-up strategy. Basically, it's when you're trying to build a spectrum block by block. Okay. First, as we discussed this morning, absorption is A water plus many other contributions from the constituents. BB is also BB water plus many other things. And we have reduced that to 3 unknowns, basically assuming A water is a constant, and that's what we have known, and then APH, AD, and AG. Further, we put AD and AG together, okay, becomes A water plus APH IDG. Still, okay, we have two unknowns. Then what we do is, okay, we try to use a spectral shape. So this symbol, okay, represent a spectral shape. We're trying to model a spectral shape of APH. We're trying to model a spectral shape of ADG. Okay, what does that spectral shape mean? Spectral shape means when we know the shape, okay, then the APH spectrum become one variable, because that means band to band, they are related. So when knowing one band, that means we're knowing other bands. So that's why I have this M1, basically it's a magnitude, okay. This is a shape. Same thing here, M2 is a magnitude. This ADG is a shape. Then we do the same thing for BB. BB water is known, then we assume we're trying to get a BBP shape, okay. Then after we know the shape, then we get the M3 as a magnitude to adjust it. So for the APH, as I showed this morning, generally, okay, generally has this kind of spectral shape. Also, it varies for different sizes, for different species, but generally, okay, it's have a bigger, larger, higher peak in the blue with a weaker peak in the red. Okay, that's from all observations like this. Then we try to model this APH shape spectrum or the shape with different number of variables. Here's approach by one variable. Okay, as Breakout did 95, basically use a chlorophyll as a variable. This APH, big A and the big B are tabulated from many, many samples. So as you can imagine, tabulated means, okay, these are from measurements. These are empirical sort of numbers. So A and this big A and this B is known, then you give a number, chlorophyll, here's a variable. Okay, you give this variable, then you get APH shape and the spectrum. What we did is instead of using chlorophyll, we use the APH 440, basically use this peak in the blue to determine the whole spectrum. Okay, so this shows when we know the p-value, then we can get the whole spectrum of APH, because this A0 and A1 are also tabulated from measurements as shown in this table. So here basically it's an example, okay, two examples showing just using one variable, we can get the APH spectrum. There are also ways using two variables. Okay, this COT did 2002. Here is the magnitude at 505. That's absorption of phytoplankton at 505. This SF is a fraction of small particles of the total. Okay, so SF is 1. That means the whole phytoplankton is picoplankton. So here's a pico, here's macro. So with this A pico and this A macro also tabulated from many measurements, basically as these two kind of like as end members. You know these two end members, and you have this magnitude at 505 and this SF as a fraction, then you also get the phytoplankton absorption spectrum. Okay, that's a two-variable approach. Here is a multi-variables approach. That's Hopper and Sassanjonas did 30 years ago. Basically, use use certain Gaussian functions to decompose the APH spectrum that can do almost 100% precise to basically to reconstruct APH spectrum. In this way, you have this lambda m j, sigma j, and this cj. Okay, basically these three variables for each Gaussian band. Okay, so you have a certain Gaussian bands, then you have basically 39 sort of variables. But unfortunately, this lambda I, this sigma j can be predetermined, okay, for many phytoplankton groups. So these two are fixed, then you still have, but basically the magnitude has to be determined. when you have 13 Gaussian bands, that means the 13 variables. So depends on your purpose. Also, we found that maybe these 13 Gaussian bands have some kind of correlation. So you can further reduce this maybe to 3 or 4. So you can use a bunch of Gaussian bands to reconstruct the APH spectrum. So that's a different ways to do this. As I mentioned, that's a way to, basically these are ways to increase the number of equations, or same time it's a decrease of the unknowns. That's for APH. For ADG, commonly, this is a common practice, although Mike has showed maybe you use exponential, use a power law can do this. Commonly these days, it still uses this exponential function with this S roughly in a range of 0.01 to 0.02 per nanometer. So we have to determine this before going in inversion. For BBP spectral shape, also Mike mentioned that this power law is no longer that good, but this has been kind of in the practice for not thousands of years, but tens of years. And surprisingly, it's working. So there may be something really, as I said many times, answer many times about the question is, can remote sensing something? My standard answer is, it's not a can or cannot, it's error bar. What kind of error bar you want? So I guess with the current standard of error bars, this power law seems okay. But certainly this eta, we have to determine it. So after we have this, we know remote sensing is a function of BB over A plus BB. So put all these modelings into this remote sensing function, it becomes 3 variables. Okay, when you have this spectrum of remote sensing reflectance, basically it's a function of 3 variables. M1 for phytoplankton, M2 for detritus gap stuff, and M3 for backscattering. This is exactly what Schuba has said 30-some years ago. It's 3 variables. So you can get to the remote sensing reflectance modeling. Okay. So then we just try to solve for these 3 variables from a remote sensing spectrum. There are ways to do it, like spectral optimization, or use lookup tables, and in other ways. So here, basically trying to, okay, say as I showed for this bottom up, see we block by block, okay, following the radial transfer, then we get it to a remote sensing reflectance modeling. Then we try to match this RS with this measured RS. That's a way to get to the M1, M2, and M3 values. Okay. So here is the example using spectral optimization. Okay, basically this shows blue is modeled RS. Okay, this red is a measured RS. This is when we, by varying the M1, M2, M3, okay, we can get a good agreement, okay, between the two spectra. Okay, this is the spectral optimization. Basically, this is this data RS. Basically, we call it either called a cost function or the error function. We're simply trying to minimize this data RS. So the logic behind this, we assume, okay, there's a unique state of this M1, M2, M3 corresponding to the remote sensing reflection spectrum. But actually, you can imagine it's not unique, because when we get to this equation, we already assumed we know the BB spectral shape, APH spectral shape, ADG spectral shape. So if you use a different spectral shape for BBP, different spectral shape for APH, different spectral ADG, you're guaranteed to get different M1, M2, M3 values. That's a fundamental sort of kind of uncertainty in remote sensing, or in ocean current remote sensing, because we simply have too many unknowns, but we have just a limited number of equations. So here I want to show you some examples of doing this in Excel, of this spectral optimization. Let's see. So here is an example. Okay, this blue, it's a measured remote sensory reflectance. This red, it's a modeled remote sensory reflectance. With here we have known A water, BB water. We hear this calling for APG spectral shape, ATG spectral shape, BBP spectral shape. Sum up of these three, then we get a total A. Sum BB water and BBP with these magnitude numbers. Okay, here's M3, M1, M2. Okay, so sum of these we get a total BB. We use a simple formula to model remote sensing reflectance spectrum, which is simply 0.05 times BB divided by A plus BB. It's a simple formula. Okay, so here you see, with this guesstimate of these three values, this modeled APH is significantly different from measured APH. So we want to change this M1, M2, M3 value to make it consistent, or at least to match this blue as close as possible. You can do it manually. That's what, when I was learning ocean current remote sensing, did that. It's a good practice. It really gets you the feeling what remote sensing reflectance, and get you a feeling which component it affects which spectral range. Let's play with this a little bit. Okay, so here we have M2 as 0.0202. You see the blue part, the model is much smaller than the measure. So we want to make it match the blue. What should we do? Increase, decrease? No, decrease, because remote sensing is inversely related to absorption. Now we have modeled RS, it's too low compared to measured, so we have to make it smaller. This way, see, it goes up. The blue goes up, and in the red part, actually, it doesn't change much because ADG has limited impact to longer wavelengths. But still, now you see, the longer part, see that this green wavelength is high, too high compared to measurements. Then what should we do? We should reduce some of these. Basically, we have to reduce the BBP. That's M3. Here, this is 0.005. Let's make it 0.003. It goes down. Okay, you see, but because the BBP impact the whole spectrum, so you see the kind of cross the wavelengths, the impact. So you can play with this for a day, then you can manually make the RS, okay, mode RS match the blue RS, but that's not a way to process satellite image, right? That will be for years to process one image. The good thing is in Excel, there is a called solver. It's a very powerful tool, a powerful, how to say, the code to do optimization. Okay, very good. It's fast and accurate. When I was doing my PhD, I tested many different kind of code or software to do spectral optimization. I found solver, even today, is still the best. Okay, Microsoft didn't pay me for this. Okay, but anyhow, okay, solver is so. I have built in this. You click solver, it will tell you, okay, what we wanted to reduce. Okay, let me get back a little bit before that. So here is the error function. Okay, so we have now between the two spectrum, the average error is 36%. That's too much between this blue and red. We want to reduce this to at least maybe a couple percent. So that's still order of high. So you will see here, let's do one more thing. Let's change this. Just watch the number, 0.36, watch the change. Reduced by half. It was 36, now it's 16 or 17%. So, and you can visually see, okay, the blue and the red getting closer compared to the previous set. So to do this automatically by computer, solver. So what solver, you define the cost function, that's M12. If you know Excel, basically M12 is a location. That's this cell, okay, that's M, column M, and the row 12. So we want to minimize this number at M12. By what? By changing the values at M6 to M8. Here's M6, M7, M8. So the computer will vary the values at these three cells with the objective for the value at M12 getting minimized. So these are already kind of set up. So let's click this solve. Just watch. Okay, so now you see the two spectrum, okay, really match each other, and which is measured by this error function, this quantitative measure. Visually, we can see they are close, okay, match very well. Error function give us, now it's under 1%. It was at sometimes 16, 17%, 36%, or even higher, but now we could optimize this error function, error value, it's just 1% between the two spectra. So that's the spectral optimization trying to give us the answer for this M1, M2, M3 sort of kind of variables. Okay, these are just an example. I will send this or share this with you guys, then you can play by yourself. Yes, yes, you can add constraints. Yes, you can do that. So let me get back to the Excel file. So in solver, you see, you can make unconstrained, or you can, here is add constraint, subject to constraint. You can add many, whatever constraints you want. Yeah. Right. But also you can make it even higher than some values. Yes. Okay, here basically the example shows how we can use spectral optimization to get answers for those variables. That's for the kind of generally for the kind of blue-green or work well for the oceanic waters. For some productive waters, there are also algorithms using the kind of red or near infrared bands, basically to look at this valley in the remote sensing reflectance. And with algorithms like 2 bands, algorithms like 3 bands, or algorithms like 3 bands. The mechanism behind this is, as we said, okay, after the modeling of these 3 spectrum, BBP, APH, and ADG, remote sensing reflectors can be read like this. Okay, in the numerator is BB water plus M3 times the BBP shape. In the denominator is M1 APH, M2 ADG plus this. In the red and the infrared wavelengths, generally this ADG has very tiny contributions. So this can be kind of canceled out, okay, or omitted, ignored. So then for the red infrared bands, especially productive waters, then remote sensing reflectance is reduced to simply M3 BBP with the denominator as A water plus M1 BP. This also because this BB water is too small. Okay, BB water is so small compared to the contribution backscattering of particles. With this, you do a ratio of the 2 bands, or you do some kind of 3-band sort of kind of algebra sort of manipulation. So here is the 2 bands ratio. The 2 bands ratio out M3. So this ratio gave us simply one variable, that's M1. So that's why, okay, using this kind of red infrared, you can get good handling or estimates of these M1 values for specific type of water. Normally it's productive waters. What that means, okay, this BB water can be omitted and this ADG can be omitted. But that's not the case for oceanic waters and not for the blue-green bands. This is really for the productive waters and in the red infrared bands. The reason is because for those kind of algorithm, it's playing with this peak. Okay, this peak is centered at 675. When you have a productive waters, this getting really high. when it's really high, then you'll get this value in the remote sensing reflectance. Basically, as simple as that. That's a mechanism behind these 2 bands, 3 bands algorithm centered on the red and infrared wavelengths domain. Okay, that's about the kind of a bottom up. Then let's talk about top down. Top down is a totally different kind of a concept or strategy compared to the bottom up. So we have remote sensing reflectance as BB over A plus BB. Then from remote sensing reflectance, the first order product should be BB and A because it's a function of A and BB. Then from this A, we can decompose that into other components like phytoplankton or CDOM or ADG. So in this kind of concept, when you know BB and A, which is the total backscattering and the total absorption, there are many other things you can do without knowing the AX. Like you can use this BB and A to calculate the attenuation coefficient, as I will show tomorrow. And you can use the BB and A to calculate light depths and calculate like circuit depths. And you can use this BBP to estimate suspended particulate matter and many other things. So that's also because remote sensing measures the total effect. What we see, for remote sensing, we don't know, okay, what's really the contribution, or we don't see the contribution of phytoplankton. It's after we decompose it, we get the contribution of the phytoplankton and other things. It's remote sensing measure total. It's a total water radiance or remote sensing reflectance. And some like others, like the water clarity or turbidity, actually is also a measure of the total effect. We see a water is turbid or their transmittance maybe say 20, 30 meters. It doesn't matter to us. It's due to phytoplankton or due to CDOM. It's just the total effect. So that's why we can use the BB and A, okay, to simply get the water clarity or those parameters. Examples of the TDS, like these publications, I listed the reference at the end. So I will use the QA as an example to show the process and the philosophy. Okay. Basically, as I said, A and BB makes the RS, including here's etc. includes the angles, sine angle, observation angle, which will make the RS different. Although not big, but it's still there will be a difference for the SATA remote sensing domain. And rough model, a crude model is remote sensing reflection is roughly about 0.05 BB of A plus BB. There are more accurate models here. Just use this as an example, okay, to show this. Then we do inversion. What is inversion? Inversion of RS basically. Here is arrow from A and BB to RS. Inversion is simply reverse this arrow. That's this row. So reverse arrow from RS, we get A and BB. So that's this so-called QAA. Okay. So data flow of QAA is you have from above surface remote sensing reflectance, we can convert to below surface remote sensing reflectance. From that RS, we can get eta. That's a particle backscattering, that's a power law coefficient. So after we know that eta, then that will be applied to this BBP power law function. Okay. Also from this RS, we can get a total absorption at some reference wavelengths. Okay, so we get A lambda 0. When we know A lambda 0, because RS is a function of BB and A. So when you know A lambda 0, then you can calculate BB lambda 0. From BB lambda 0, BB water is known, is constant. So that will give us the BBP lambda 0. So basically, from this step to this step, it's algebra. Okay, it's precise. As long as that we believe that remote sensing reflectance is a function of BB over A plus BB. Okay. After we know BBP at a reference wavelength, and BBP is modeled as a power law function wavelength, and this eta is null, then we can propagate BBP number 0 to BBP at shorter wavelengths. Because as long as we believe this model, then we get BBP at other wavelengths. After we know BBP at other wavelengths, since we already know BB water at other wavelengths, so we know BB at other wavelengths. After we know BB at other wavelengths, then we can get A at other wavelengths, as long as there are remote sensing reflectance at that wavelength. So basically kind of iteration, but iteration is from one wavelength to the other wavelengths, starting from lambda 0 to the other lambda. So in these steps, these green steps, they are algebra calculations. And after we know the total absorption, because total absorption, as we said, it's a sum of 3 components, okay, with here's APH, ADG. So at least we have 2 blue bands for all the satellite sensors. You have 11, 411, 443. So now we have 2 equations with 4 unknowns. This psi is APH 411, 443. This another, I also plus psi, so it's another ratio. So you have this 2-0 ratio and these 2 values, APH and ADG. So if we can estimate this and these 2 ratios, then it becomes 2 equations, 2 unknowns. That makes this set of equations could be solved. So that's the whole data flow of this kind of top-down sort of kind of system. The logic behind this estimation of A number 0, as you can see here, the key is getting to A number 0, because only after we know A number 0, we can calculate BBP number 0. Why we can get estimation of A lambda 0? That's because total absorption, it's a sum of the A water plus other things. And A water, as I showed this morning, it increases with the wavelengths. And at a longer wavelength, it is dominated by A water. Okay. So for instance, here is sort of kind of 3 examples with chlorophyll, C4 chlorophyll. One is 0.03, another is 1.0, 5.0. You can see. This open circle is pure water absorption. This blue is chlorophyll as 0.03. Here's chlorophyll as 1. Here's chlorophyll as 5. So for chlorophyll varied by almost 300 times, you see big change of total absorption at the blue band. Okay. But the change of absorption, total absorption at the green band and the red band, it's limited. That's because water itself dominates. For instance, for this case, if we select 555 as a reference wavelength, let's say without any training in ocean optics, we pick a number. We'll just simply blindly pick a number, say 0.07. Okay. Here the range is about 0.05 to 0.12, something like that. So we pick a number of 0.07. Yeah, we are not accurate. But that error, it's roughly about 20–30%. It's not, say, wrong by factor of 2 or 3 or order of magnitude. That's 55. So that means we can just with blind, we pick one number. It's not that bad. We can even do better at a longer wavelength. Here is 640. See, with chlorophyll varied by almost 200 times, A640 varied roughly about within 10%. So that means, okay, we can at least make the accuracy to within 5% if we simply pick an average between the higher value and the lower value. So we can generally get a good handle on the absorption at lambda 0. Then you may ask, why we not go further to the red or infrared? Yes, theoretically we can, but practically we cannot. The reason is, get to a longer wavelength, the absorption is too high, then less photons coming out of the ocean. Then that means your remote sensing reflectance has lots of uncertainties. When you have that has a high uncertainties, you put an accurate absorption into the equation, to calculate BB, that the BBP has tons of uncertainties. Use that has tons of uncertainties. They propagate it to the other wavelengths. Those uncertainties will propagate it to the other wavelengths. So here, basically, it's a compromise. You have to choose this reference wavelength between the measurement and the accuracy. So for the open ocean, because generally remote sensing reflection at 555 can be very well from satellite, can be very well calculated. So we use at open ocean, we use 555 as a reference wavelength. When we get to coastal waters, because signal is getting stronger in the longer wavelengths, you may switch that to 640 or even 670. Okay, or that depends. So for the QA, there are lots of variants. There are some studies even using 750 for really turbid waters, using 750 as a reference wavelength. So in short, when we know the absorption reference wavelengths, we can calculate BB at reference wavelengths from remote sensor, then propagate to other wavelengths. We can get a spectrum from RS spectrum. So that's the logic behind this. And in these steps, you see that there's no spectral modeling of the APH or ADG. Simply, there's only one modeling, it's the BBP. We have to use the BBP power function or any other function as long as you think is valid to propagate the BBP from one wavelength to the other wavelengths. Then let's get back to the reference wavelengths, the absorption reference wavelengths. I mentioned moments ago, yeah, just pick one number, but that's not, yeah. We know that varies from water to water. Why we should use a fixed number? We should use a dynamic number. Okay, data vary from water to water. So this is a empirical function for get A550, okay, with this chi as a bunch of RS, okay, in it. Don't ask me why. There's no why for these kind of regressions. It is just empirical. I have the data set. I tried all the combinations to fit. It found out this one fits well. There's no why. Okay. Yes, but then you will, for that case, as long as your remote sensing reflection measurement is still good in the longer wavelengths, for that case, you will move this number 0 to longer wavelengths. Yes, yes, yes. So the case, as I mentioned, is a compromise. It's a compromise between the precision of A number 0 versus the precision of RS. So we are trying to, okay, get that compromise, or basically trying to able to calculate something with our acceptable sort of uncertainty. Yeah. So here is basically how we get this A550. Okay, for most, I think for 90% of the global ocean, this works fine. Okay. Interestingly, recently I have grad students trying to use neural net to beat up this regression. They found out neural net cannot. I'm surprised. I'm still asking them how could the neural net cannot beat this empirical relationship? They haven't given me a good answer yet. Anyhow, so that's an empirical way to get the reference, get the absorption at 550. So here is basically shows, okay, for A550 in a range of all the way to 0.15, A550 to 0.15, that covers 95% of the global ocean or natural waters. So we can get really good estimate from that regression. So that means for this part, okay, as long as RS can be measured well at 550, then we can get a good handle of this reference wavelengths. Then, okay, we have remote sensor reflectance, and then we can convert it to below surface. We have this RS okay, this Gordon's formula, okay, then from this polynomial, this is a polynomial, yes, then we can get this U, which is BB over A plus BB. Okay, this can be calculated from remote sensing reflectance, and we know A550, then BB550 can be calculated algebraically because we know U, we know A, then we can calculate BBP550. When this is known, but we have to propagate BBP to basically to the shorter wavelengths. Generally, we don't propagate to longer wavelengths because I said when you have this reference wavelength as 550, that means already we don't trust the RS in the longer wavelengths. So at this time, you propagate this BBP from 550 to 700, 750. Yes, you can, but you cannot use that RS at 750 to invert A because RS at 750 is no longer that trustable. So that's why normally we propagate this BBP from a reference wavelength to shorter wavelengths or to high quality RS. But still, for this propagation, we need to this number eta, or I call it Y because I call it Y. It's basically I don't know how to get that. Has to be some way to get this power law coefficient. So here is another empirical. Again, there's no Y. Basically, these dots are come from measurements. Okay. This x-axis is a ratio of RS 443, 550. Okay. As you can see, the fit is not that good. Okay. Here it varies by a factor roughly about 1.5. It's not that good. But at least as that if we trust the measurements, that shows the eta, actually the high number for the open ocean roughly is around 2. I think that matches Schuba's paper 1989. He also mentioned range is roughly up to 2. So this for measurement also shows basically here when for this ratio as high as 4, that's oceanic waters, oligotrophic waters. For oligotrophic waters, the high number is around 2. For this kind of turbid waters, for measurements, it is everywhere. It as low as 0 and as high as 1.5. I have no idea which one is right or wrong because that it's not easy to accurately measure BBP spectrum. Okay. Anyway, from this data, what we have at that time, we use this formula trying to get guesstimate of eta. Okay. You see, it's not that good. Fortunately, doesn't matter that much because that eta is applied to the ratio wavelengths. Okay, let's say our interest is say 440. 550 divided by 440, that ratio is roughly about 1.1. Okay, 1.1, if this eta, the true number is 1.0. So this ratio with 1, that's still 1.1. If our guesstimate is wrong, we get a guesstimate of 2. So 1.1 becomes 1.2 after you apply the 2 there. So 1.2 versus 1.1, that's only a 10% difference, even to 440. Okay, so that means, okay, this eta can be wrong by 50%. That percent has limited impact after it applied to this ratio. But certainly we want to get this eta as accurate as possible. But at this point, since we don't know what is really this eta in the natural world is, so this guesstimate, although it's not perfect, its application to that ratio wavelength, the impact is limited. So that's why we can still use this way to do the calculations. Actually, I just showed this morning, the neural nets to estimate this eta, which is way better than this. But the improvement to the retrieved A and BB, it's limited because, as I said, it's applied to this ratio, not directly applied as a magnitude number, sort of thing. Okay, now we have BBP and we have BB water that give us a total BB. Then when we know total BB, A, and we know U, then A can be calculated. So that's also algebra. Okay, A is A water, APG, and ADG. We have 2 bands in the blue 410. Let's say use 410 and 440 as examples, but still it's 410 has APH 410 and ADG 410, APH 440 and ADG 440. So we still have 4 unknowns, 2 equations. We have to somehow get a shape based on ratio of 410 divided by 440. That's this one, and here is this one, ADG 440, APH 440. So plug in here, then get this 2 equations. Then we can solve these 2 equations. ADG 440 is this. APH 440 simply is the total A minus A water by ADG 440. Now, as you can see, we still need to know these 2 numbers, which are the ratios of APH 410 divided by APH 440 and ADG 410 divided by ADG 440. Again, empirical. Okay, generally speaking, APH 410 or 412 divided by APH 443, it's in a number. Okay, smaller than 1.0 and in a small dynamic range. Okay, so as shown here, it's not vary by order of magnitude. It's in a small range. So we used a simple formula trying to estimate this. And then for that ADG 410 divided by ADG 440, it depends on that spectral slope, S. Okay, here is the S from sample measurements. As you can see, roughly, it's also in a really wide range, all the way down to about 0.01 to 0.025, but it's really concentrated around this range, roughly about 0.016. So we have this kind of formula, empirical. So all these are empiricals for this ratio or for this spectral shape related parameters. So that's why this is quasi-analytic. It's not truly analytical because there are a bunch of parameters. It's just impossible to get analytical. We have to assume something to get something. So that's the closest thing to be an analytical algorithm. So as we see, APH can have different shapes, ADG have different shapes. So there are ways to try to get a range of solutions, so-called ensemble solutions. Like Wang did it with Emmanuel Boss, and then recently also just later on also did that. Basically, use many APH shapes and many ADG shapes. Okay, each will get a set of M1, M2, then trying to get ensemble solution, which will give an average and get a sort of kind of standard deviation. So that's called ensemble solutions. So here is a chart shows the kind of many steps to get the ensemble. So the good thing is eventually the average pretty much matches that directly from QA, but these ensemble solutions will give you a range of solutions. Okay, now you can see, I always want to show this. Okay, from this kind of quasi-analytic sort of kind of a formula or system, we can calculate A, calculate BB. But you also see products of chlorophyll, as I showed at the beginning, as a ratio of remote sensory reflectance. So what is this ratio derived chlorophyll? So chlorophyll is a ratio of RS. RS is BB and A over A, BB over A plus BB. So you can see this ratio of RS of 2 bands is actually of this BB and A, their ratios. So not surprising. Chlorophyll products is actually IOP product because it's by the model, by the mathematics, it must be one kind of IOPs. So when you look at the ratio divided chlorophyll in the South Pacific gyre, you can see this is analytic derived or semi-analytic derived total absorption. This ratio divided chlorophyll, the regression is almost 1 because it's all come from the same remote sensory reflectance. And globally, if you look at models, this globally derived A443 for QA, this ratio divided chlorophyll, you can see also highly covariant. So ratio divided chlorophyll, as I call it, basically it's a rescaled, okay, total absorption coefficient. Okay, when we process oceanic waters, and as Mike also mentioned a little bit about the inelastic scattering, Raman scattering, because Raman scattering will contribute photons to the green, to the red. But when we use QA, we use RS at the green band, 50 to 55, to calculate BBP. If we do not remove that Raman scattering, that actual photon will be accounted as actual BB particle. So we have to do a correction of the Raman contribution, especially that's very important for oligotrophic oceans. So here is a kind of analytical solutions for remote sensor reflectance. Okay, it's quite complex, and you have to do that is do it iteratively, because it require KD, require BB, all those things. So you do iteratively get IOPs, then do the removal, and then calculate again. Another way to do a simple approach is calculate this total. This is called Raman factor, and the Raman factor basically it's related to the water properties. That is related to the RS total. So you have, when we have this alpha and beta 1, beta 2, then we can get this Raman factor. Put this in, then we can get this Raman contribution be removed. We're trying to process remote sensor data in the oligotrophic ocean. So basically, this example shows, okay, if low Raman correction, the BBP, okay, will be shown by this blue. Is much higher than the relationship between log BBP and the log chlorophyll, okay, for this black and basically these black lines. After removal, then it moves much closer, okay. So that's basically trying to emphasize for the open ocean, okay, it's very important to remove the Raman contribution. Okay, that's about the two strategies of algorithm, mechanics algorithm. Any questions? Okay, if not, then I will move to the part about impact of the sensors. Because when we apply algorithms to satellite, there's so many satellites. Okay, we have MODIS, we have WIRS, we have MERIS, OC, we have even NANSAT. Okay, each sensor has their own spectral, or basically sensor specs. Spectrally, they have number of bands, position of bands, and the width of bands. Okay, you have each sensor has that. Then each sensor has its own signal to noise ratio. Okay, each sensor has a different spatial resolution. NANSAT is 30 meter by 30 meter. MODIS is 1 by 1 kilometer by 1 kilometer. Okay, so they have different pixel size. Okay, then GOSI, it's geostationary. Each day can measure 8 times, 10 times, but the MODIS or OC normally for the low latitudes once per day. So have different temporal resolutions. So it's important to have a good feeling and understanding of, okay, what these sensor specs will impact to our retrievals. First, look at the numbers. Okay, here a study 20 years ago. It shows that x-axis is an inverted absorption at 440 for resolution at every 5 nanometer. Okay. Y-axis is an inverted A440 with E10 means every 10 nanometer. E20 means every 20 nanometer. Here is the MERIS bands, MODIS bands, CWIS bands, MODIS 2. MODIS 2 basically is either 640 there. MODIS here, MODIS without 640. So as you can see, okay, for wide range, okay, all the way from 0.0 something, that's basically blue water, to really coastal turbulent water with absorption as a 440. Every 5 nanometer versus every 10 or 20 nanometer, it's nearly identical. Nearly identical, okay. Even for all the way to, if we look at the kind of oligotrophic ocean with A440 up to 0.3, basically this range, okay. So all the satellites pretty much give us similar results. So these bands, okay, their impact is really depends on the water. If to really turbulent waters, we need more bands, okay. But even more bands, 5 nanometer band versus 10 nanometer band, the difference is small. This is total absorption. Here is the phytoplankton absorption at 440, okay. This also, again, here's every 10 nanometer, this solid circle, and E20 is every 20 nanometer. Okay, basically here is a wide range from oligotrophic ocean to kind of a coastal water. Here's a kind of zooming in to this range. Okay, so you see, again, for every 10 or every 20 nanometer, its results is roughly identical to every 5 nanometer. That's so here's for AG or ADG, similar conclusion. Here's BBP at 640, similar conclusions. And here is if the shallow water is bottom depth. Here's every 5 nanometer, and H is every 10 nanometer. No, H is many other kind of a spectral sort of resolutions. As you can see, every 10 nanometer, the results almost identical to every 5 nanometer. But other bands, like say C-waves, MODIS, or MERIS, they have different results because when it's shallow water, optically shallow water, it's more complex. So basically, this says, okay, retrievals of remote sensing reflectors with every 15 bands, like basically more than MERIS. MERIS, I think it's about 7 or 9 bands in the visible. So we add more, make it the 15 bands. Those retrievals of 15 bands is roughly equivalent to every 5 nanometer. Why is this? Why only a few bands seems get similar results as 80 bands? Every 5 nanometer from 400 to 700, that's 81 bands. Okay, 15 bands kind of equivalent to 81 bands. That's kind of mind-boggling. Actually, it's not. So we look at this with data measured globally, oceanic waters and the coastal waters. We get about 1,000 remote sensing reflection spectra, where this shows the wide dynamic range of these measurements. Then we look at the correlation of different bands based across the band. What this figure shows, the top black, it's correlation of, say, every 5 nanometer, 400 versus 405, 405 versus 410, 410 versus 415, and on. So that's this black dash line. Every 5 nanometer, look at band-to-band RS correlation. The red, it's every 10 nanometer, basically 400 versus 410, 410 versus 420, 420 versus 430. So, and so on. That's every 10 nanometer, every 20 nanometer, every 25, and so on. So the bottom is every 30. So what this tells us, for these many natural waters, the remote sensing reflectance from band to band, if the gap is just 5 nanometer, it's highly correlated. It's rough to, so here is 0.98. This is basically is close to 1. Even at 10 nanometer, it's still highly correlated. That correlation drops when it gets to 25 or 20 nanometer. So that tells, okay, when you have more bands, it's redundant measurements, not necessarily really independent information. That's why, so every use 15 bands versus 80 bands, roughly we get the same kind of similar retrievals. This also, because of this, as we showed with IOPs, for ADG and APH, they're not like those properties of the atmosphere. The atmosphere, they have those kind of, it's as Darius told this morning, those are kind of at the atom and the molecular level, okay? So they have sharp peaks at specific locations. Yes, yes, basically, that's another study, basically how to determine the best bands. To determine best bands is to look at the remote sensing reflection, look at the curvature. You're really trying to catch the maximum minimum, okay, and also capture the turning points of a curve. So that's I have a few slides I can show you later if I have time, okay. So the reason for this kind of high correlation between neighbor bands, that's because for this APG and the ADG, they are really they do not have sharp peaks or sharp valleys. They are kind of really broad effects because they have different kind of energy style or energy level, as Darwin showed this morning. So you see, APH basically in general has this kind of spectral shape. There are low sharp bands, suddenly say 440, then another sharp valley, say like 475. No such, it's a smooth, broad effect. ADG is even worse. It's really monotonic function from shorter wavelengths to longer wavelengths. And no matter how you change the S value, it's still highly basically correlated for these wavelengths. So that's why, okay, for ocean optics, ocean current remote sensing point of view, this band-to-band correlation is very high of remote sensing reflectance. Okay, that's about the band thing. So then if we pick 15 bands from 400 to 700, these are the red. Okay, we use this red RS to construct a hyperspectral RS to every 5 nanometer. As you can visually see, this reconstructed RS almost match the black, almost exactly. Also, you can see the tiny difference. Here's a way to quantify that difference. Correlation coefficient between the reconstructed RS and the measured RS from 400 to 700 is very close to 1. Then the average absolute percent difference generally is under 3%. At around 685, there'll be higher difference. That's because the fluorescence. Okay, the fluorescence is different animal, so there's no good handle of the so certainly you want to design bands, you want a band at the fluorescence peak about 681. So generally for the blue to green, the reconstructed RS matches the measured RS very well using 15 bands. Okay, so that's about band numbers. Band width, we have to also keep that in mind. Okay, so here is a hyperspectral measurement. Basically, that is a field radiometer, so it has a resolution of 5 nanometer, so you can get this continuous measurement. But for other sensors, the bandwidth here I use the example is very high, like NISAT 8. NISAT, the band 3 is this wide. So when you have a measurement at this band with this kind of bandwidth, then it is the average of this sharp drop and this flat. So it cannot resolve this curvature of remote sensing reflectance when you have a bandwidth like this. Same thing for this blue band here, then it's average of these peaks and these kind of drops. So the bandwidth really, when it's too wide, it loses lots of spectral information. But still, people want to use the NISAT measurements to calculate IOPs. Then we go back to this model where BB water and A water. Then for this NISAT sensor, you still have to determine a BB water number in order to be used in this model. You also need a A water for that band in order to do the calculations. But BB water goes like this, A water goes like this. So how to get the band average A water and the BB water? That become a question, okay, or an issue. Traditionally, it's kind of treated like common measurements, like radiance measurements. Okay, for A water, we have the spectral A water, use a band response function, do a basically integral. And here, basically, it's an integral of the band response function. So then get the kind of band response function averaged that absorption for that band. So for each band, you get A water. Commonly is doing like this. And this is, I'm not sure still NASA using this. Basically, this number is what I got from NASA's tables. As you can see, for MODIS, it's a band average A water is this. For WIRS, the band average A water is like this, these triangles. The reason because Wills has a narrow band of 10 nanometer, but it has this called auto band response. The auto band response is all the way to 800, 900 nanometer, even for 12 band. But for 800 nanometer or 700, that A water itself, this number is very high. This number high put this response function into this integral, so to propagate to the A water band 1 of Wills. If we put this kind of number into the modeling, then there'll be no closure because that A water from this response function or autoband response is too high. So here is measured RS, this blue, then you get you model A water, you plug in, it will drop greatly because that A water from this band average is too high. If we look at this model again, remote sensing reflection is BB over A, or BB over A plus BB. A water is in the denominator. So when you have a high absorption, okay, in the longer wavelengths, its contribution to RS actually it's really tiny, okay, or in other words, no contribution at all, okay. Say RS at 800, that contribution from the response function to RS at blue, it's minimal, okay. So a correct way we think it's because RS inverse function of A water, so we have to do an inverse of A water first. Plug in the response function, get the band average reverse value, then reverse this back. That gives us the band average A water, okay, for this band width effect. With this, then we get the A water for C waves model Wills band average A. It's roughly very close to the hyperspectral A water. So basically, this shows the band effect, okay, the band width effect on A water on those constants. Plug these numbers into a model, then we get much better closure between measured RS and model RS. So that's on the bandwidth effect. Okay, then spatial size or pixel size. Normally, it's like a modis, it's 1 kilometer by 1 kilometer. Line sight, 30 meter by 30 meter. Yeah, for the open ocean, we can think within the 1 kilometer is spatially homogeneous. Okay, but in nearshore coast waters, within that 1 kilometer, it might be like this. Okay, so high spatial kind of variations. Then let's suppose we have a boat measured each these subpixels, get their chlorophyll concentration. Then we want to use these values, compare that with the chlorophyll from satellite retrieval. Should we? How to do this? Should we simply average the chlorophyll of each subpixel and then compare that with this big pixel? Yeah, certainly it's average because this is a big this large pixel, we will have subpixel variations. Then we have to get the variations and get an average because to match this size of the area. Then how to do the average? And what kind of average? So look at this. We know remote sensing reflection is LW over ED. LW of low resolution is an average, arithmetic average of high resolution because we measure light coming from this area. Okay, it's a collection of the output photons of these each fine subpixel or sub areas. So LW, low resolution, this for LW, it's a LW of high resolution. Okay, it's arithmetic average. ED for this area is certainly the same. Okay, as long as so it's not say 1,000 kilometers wide. So ED will be the same. So now we can see remote sensing reflections of low resolution. It's a arithmetic average of remote sensing reflections of high resolution. Okay, that's for sure. Now, if we look at RS is over is a G over it's a basically this is some kind of a modeling coefficient times the BB over A plus BB. So now you can see an average of RS does not mean this absorption of low resolution is an average absorption of high resolution, because this A is in the denominator of this RS. And we just mentioned that chlorophyll is simply some kind of rescaled total absorption. Then this chlorophyll of low resolution, it's not arithmetic average of chlorophyll high resolution. Think about this. Okay, you have in this subpixel, you have one with low chlorophyll, another with high chlorophyll. The high chlorophyll one will draw down the blue band RS. The low chlorophyll one, because of small absorption, will have more photons come out of blue. So RS will be tilted to the low RS, to the low chlorophyll, because it has higher RS. Okay, it's an inverse relationship. So for the RS, average RS actually see more of brighter photons, see less of the darker photons. So eventually, that's why, okay, from RS, for this kind of subpixel variations, it will feel smaller or lower chlorophyll than the arithmetic average of chlorophyll. If we do it mathematically, say here's the RS of low resolution, here's the average of RS of high resolution. Each one basically it's BB over A, simplified. Okay, you do some kind of algebra. Basically, eventually this A low resolution, it's weighted by the backscattering of the subpixels. As I mentioned, if you have a pixel, okay, if you have a pixel with high backscattering, that means more photons come out from that high backscatter one. So that will have more weight to the measured total signal. So that's why we see here, this low resolution absorption is really weighted by BB. So backscatter weighted average. But BB pretty much is arithmetic average of the high resolution. That's because, as I showed in the QA solid state approach, in the longer wavelengths, the absorption is pretty much a constant. It's dominated by A water. So what we see the RS, basically that average is proportional to the average of BB. So that's why BB also, because also it's in the denominator. Okay, so BB of low spatial resolution is pretty much an arithmetic average of high resolution. That's why for this one. So here, basically showing examples. We have 4 RS. Okay, this dot, this green, and this red, this cyan color. This black basically is the average, okay, of these 4 RS, which has same backscattering coefficient but different absorption coefficient. Okay, here this sign is the retrieved A of total absorption from this black RS. This red is simply arithmetic mean of the absorption, okay, from these 4 curves. Now you can see this red is significantly higher than this low resolution or retrieved values. As I mentioned, that's because, okay, for this remote sensor, it sees more contribution from this cyan color. It has less contribution from this black, or this, sorry, not black, this red. So it's a weighted average. However, if you, here is the dotted line, it's the formula, it's this formula, okay, weighted average. The weighted average then match the retrieval, okay, from this RS then very well. Here I showed another mean that's called a geometric mean. Basically, it's you times all of them, then do the root back. So still, even no matter the arithmetic mean and the geometric mean, they will be higher than the retrievals of this low resolution sensor. For shallow water, similar thing. Okay, you have a near slope. Okay, near slope, you have a core sensor. It will see the edge. It will see one side of the shallow one, another side is showing deeper one. Within a pixel, you'll get a number of retrievals, right? Assuming the retrieval algorithm is perfect. then that retrieval depth, think about it's an average of these shallow depths and the deeper depths. Certainly not. Again, because remote sensory reflectance of shallow water, it's inversely related to depth, as showing this exponential function. It's a negative. Okay, I think John will show more in a few days. So the details. So remote sensory reflectance, it's inversely related to the depth. Okay, so certainly you retrieve the depth of that. Okay, with subpixel vibrations cannot be a simple average, arithmetic average of the shallow side and the deeper side. Another way to look at this, put it extreme. Okay, you have a pixel. Okay, it's a cliff. Half of the pixel is say about 2-3 meters. Okay, deep. But then after a cliff, it gets to 100 meters. Okay, 100 meters with for this side, there are lots of photons from the bottom. For this side, you have no photons from the bottom. So your average of RS certainly will be tilted to the shallow side. But when you do the simple average of the 100 meter and 2 meter, you get depth of what? About 40 or 50 meters. As simple as that. So because there is inverse relationship, then the retrieved depth also seems like a retrieved absorption. It's not a simple average of these subpixel values. So here is basically, we show that after some simplified approximations for same type bottom, this low resolution depth, okay, for H low, it's an inverse of the H high, then inverse back. Because basically that shows, okay, you have 100 meter, the 100 meter, it's inverse, has less weight in the total formula. Okay, it's the shallow ones has higher weight to this sum, okay, or to this average. Here basically also examples shows here's a low resolution retrieval depth versus a weighted mean, this arithmetic average, this geometric average of these 4 examples. Basically the concept is when it's a reverse relationship remote sensing, then you have to do a kind of weighted average, or you have to emphasize the pixels with a higher contribution to the total signal. So to summarize, many algorithms for IOPs have been developed, but certainly we're expecting more and better ones. So it's an ongoing process. And as I said, the bottom-up strategy basically is trying to get every component, okay, first, and at the same time get a total. Like say, when you get an APH and ADG, certainly you get a total A, but it's a kind of one strike or one action get all the components. But still, in that process, you have to specify each component on the modeling. But in this step, then, as I mentioned, the APG shape, ADG shape will impact your results. So really highly depends on the bio-optical models. For the top-down strategy, because it's get the total first, okay, then decompose separate other components later. It really depends on necessity. For some of the applications, if you don't need the APH ADG, then you stop at the total A, okay, or total BB. But for this kind of process, it depends on accuracy, because we are doing exact calculation of BBP at that reference wavelength. Think about it, if that reference wavelength, the RS is wrong big time, then that will have an impact to the total whole inversion for the QA. And special details, as I mentioned, the number of wavelengths, bandwidth, all these have impacts, okay, to the IOP's retrieval. So you certainly want to have more bands, but not necessarily really have band at every 1 nanometer. But on the other hand, I'm not against you have a sensor have more bands, but that adds to the storage, adds to the data transmission from satellite to the station, with the receiving station. So also these are kind of compromise. In the early days, why we have CZCs only 4 or 5 bands, that's because this kind of technical sort of kind of limitations. Now, when we have this kind of, we resolve the technical limitations, we have tons of storage, go for it, as long as it's kind of feasible. Spatial variant properties, we have to be careful, okay, with the pixel sizes and the sub-pixel variations. As I just showed a bunch of examples, many situations, it's not simply an arithmetic average. Okay, again, I have a bunch of references.